Hello and welcome to this video for CE 105-205. So in this video what we are going to talk about is to talk about Chalcogenide glasses. So far we have been mostly talking about oxide glasses, glasses that contain some oxygen atoms, but oxide glasses are not, despite the fact that oxide glasses is pretty much the majority of commercial glasses. Most commercial glasses are oxide based. They contain some oxygen, for example silica, B2O3, P2O5, etc. Some other glass, the glass that don't have to be oxides, some other glass can be based on other elements and may not contain oxygen atoms. And one example of such glasses are the Chalcogenide glasses. So what are Chalcogenide glasses? Chalcogenide glasses are glasses that will contain as at least one element, of this glass will be made of a Chalcogenide element. So Chalcogenide glasses can be made of alloy, they can be made of different elements, just like oxide glasses, which can be made of oxygen, silicon, aluminum, sodium, etc. In the case of Chalcogenide glasses, usually it will be made of several elements that are alloyed together, but at least one element is going to be a Chalcogenide. So where the Chalcogenide are the elements of the column 16 in the periodic table. And so in this case, the Chalcogenide would be sulfur, selenium, or tellurium. Oxygen is also in this column. Oxygen would also be a Chalcogenide element, but if a glass contains some oxygen, then it's going to be an oxide, not a Chalcogenide. So in the case of Chalcogenide glasses that are not oxide glasses, then they would contain at least a portion of sulfur, selenium, or tellurium. Usually, those are not going to be the only elements that are present in the glass. You will typically find some other elements that are part of either column 14 or column 15. So for example, in the column 14, you would find silicon. So silicon can be present in Chalcogenide glasses. For example, in silica glasses, silicon is mixed with oxygen to form SiO2, but silicon can also be mixed with selenium or sulfur or tellurium. So, and in that case, it's going to form a Chalcogenide glass. So in the same column, we also have germanium. Germanium is in the same column as selenium, and tin would be another example. We can also have sometimes some elements that are from column 15. So in that case, you can have some phosphorus, some arsenic, or some antimony. So those are the typical elements that you would find in Chalcogenide glasses. It can be either a binary mixture or maybe a ternary mixture. So for example, you can have a mixture of, let's say, for example, germanium, selenium would be a common mixture, or you can have arsenic, selenium would be also a common types of Chalcogenide glasses, or you can have a mixture of everything. You can have a germanium, arsenic, selenium ternary glass. That would be a ternary combination of those three elements. So if we compare what we have seen so far, which is oxide glasses, and what we are going to see now, which is Chalcogenide glasses, there are some key differences between those two types of glasses. So the first thing, as we mentioned, is that oxide glasses necessarily is going to contain some oxygen, while Chalcogenide glasses will not contain any oxygen. Instead, it will contain some selenium, some sulfur, or some tellurium. So that's going to be the basic ingredients of those glasses. The second thing is that in oxide glasses, the oxygen is typically negatively charged. It has typically a partial charge of -2. It means that the oxygen will typically steal 2 electrons from its cation neighbors, and it's going to be contained, it's going to be mixed with some cations that are going to be having a positive charge. So in oxide glasses, atoms are going to be charged. They're going to be equivalent to some cations or some anions. In the case of Chalcogenide glasses, when you have those selenium, germanium, arsenic, etc., those things are going to be neutral elements. In that case, those chalcogenide glasses, they tend to form covalent bonds, and in covalent bonds, the electrons are not shared in between the two atoms. The electrons are just delocalized between the two atoms. So in this case, each of those atoms will be neutral. There won't be an excess of negative charge on the oxygen and a deficit of negative charge on the cation. In this case, all those atoms will just simply keep their charges and will remain neutral. And this has some important consequences, because the fact that atoms are charged in oxide glasses has various consequences. The first is that in oxide glasses, you typically have a fixed stoichiometry. What does it mean? It means that, for example, if you do a mixture of silicon and oxygen, you can have only one composition in oxide glasses, which is SiO2. This is because, in this case, silicon would have a charge of +4, oxygen would have a charge of -2. So the only way to make these types of glass neutral is to have 2 oxygen for each silicon. That's the only way you can make this neutral. In chalcogenide glasses, because all the atoms are neutral, you can have a variable stoichiometry. You don't have to have a fixed composition. For example, if you take a glass that is a germanium selenium glass, you can have any fraction x of germanium while the rest will be selenium. You can have variable stoichiometry, which means that you can have like, for example, a GSE2, which would be the equivalent of an SiO2, that would be structurally equivalent to an SiO2, but you can also have a GSE4 or a GSE8, or you can have any stoichiometry. You can have any fraction x of germanium and the rest being of selenium. Or you can have also pure selenium with x equals 0. All of those stoichiometry are possible because, again, there is no charge, so the system doesn't have to, it's always neutral, whatever the stoichiometry is. And the other consequence of the fact that those atoms are neutral in chalcogenide is that in oxide glasses, because the cation are always positively charged and the oxygen is always negatively charged, you always have heteropolar bonds. So what does it mean is that in oxide glasses, you will always find bonds between the cation and the oxygen. You will never find a bond between 2 oxygen or a bond between 2 cations, because those two are negatively charged or positively charged. So you cannot have 2 cations attached to each other or 2 anions. There will be a strong Coulombic interaction. So in this case, all the bonds will be heteropolar, where a cation is necessarily connected to only oxygen, and oxygen are necessarily only connected to cations. In chalcogenide, you don't have such requirement. You can have either heteropolar or homopolar bonds. You can have both cases here because there is no requirement. So you can have, for example, some germanium bonds, or some selenium bonds, etc., or some germanium-selenium bonds. Everything is possible. Certain bond will be favored at the expense of the other, but still, in this case, since the atoms do not have any charge, there is nothing that prevents the formation of selenium-selenium bonds, for example. And for example, if you take a pure selenium glass, then necessarily all the bonds will be selenium attached to another selenium. So those homopolar bonds are only available and only allowed in chalcogenide glasses and would not be allowed in oxide glasses, where only heteropolar bonds are allowed. So those are some key differences. And because you have those key differences, then it means that the structure of oxide glasses will not be the same as the structure of chalcogenide glasses, because of the fact that you have this variable stoichiometry and the possibility of forming some homopolar bonds. So when it comes to describing the structure of chalcogenide glasses, there is an important characteristics of those glasses, which will be the coordination number of each types of element. And in this case, that's important because it's going to give you the number of bonds that are created by each types of element that is incorporated in the chalcogenide glasses. And usually In chalcogenide glasses, it's not always the case, but most of the time, or at least very often, atoms in chalcogenide glasses will follow the 8 minus n rule to define their coordination number. The 8 minus n rule tells you, it's a rule that tells you the coordination number of a given element. And the idea in this case is that you first need to know n, where n is the number of valence electron of an element. And what this rule tells you is that in that case, the coordination number of this element is going to be given by 8 minus n. And the idea in this case is that this coordination number will correspond to the coordination state that will enable this element to reach the state of a perfect gas, with where all the electronic orbitals are fully filled, where this element would be now surrounded by 8 electrons, just like a perfect gas. So to apply this rule, you just need to know how many valence electron a given atom has. And so this only depends on which column of the periodic table it is. So if you are on column 14, so column 14 is when you have, for example, silicon, germanium, or tin. So those column, in this column, those atoms have 4 valence electron, which means that in this case, their coordination number is going to be 8 minus 4 equals 8. So we already knew that, for example, silicon have a coordination number of 4. They tend to form a tetrahedron. That's the same for germanium. That's going to be the same for tin. Now, if you move one column to the right, so you move to column 15, now on this column you would find phosphorus, arsenic, and antimony. Now, the coordination number, the number of valence electron would be 5, which would give you, in this case, a coordination number of 3. So 8 minus 5 equals 3. In this case, note that phosphorus, when phosphorus is as an oxide, it doesn't follow this 8 minus n rules. This is an exception to the 8 minus n rule when phosphorus is combined with some oxygen to form a P2O5 glasses. Then phosphorus would have a coordination number of 4, which would violate this 8 minus n rule. But for when it's used as a chalcogenide, then and if it follows the 8 minus n rule, then for arsenic or antimony, they have 5 valence electrons, so that gives you a coordination number of 3. And so, for example, if you take arsenic, it means that in this case it's going to form a trigonal structure like this with 3 atoms around them, 3 neighbors. And finally, if you move to the next column, the column corresponding to the chalcogenide element, then those column is the one that contains sulfur, selenium, tellurium. So in this case, the number of valence electron is now 6, which gives you a coordination number of 2. So it means that in this case, for example, selenium would have just 2 neighbors. So in this case, if you summarize, in the case of selenium, you would typically have an angle of 109 degrees. And in the case of arsenic, since it's forming a trigonal structure, it's going to form typically about an angle of 120 degrees. In the case of selenium, it's the angle can be a little bit more variable. Typically, the angle is going to be less than 180 degrees. 180 degrees would be the angle that maximizes the distance between the 2 neighbors, but usually in selenium you also have 2 non-binding electrons, so usually you will have an angle that is closer to somewhere between 109 to 120 degrees. So those are different coordination state that you will typically find in chalcogenide glasses. So one typical example of chalcogenide glasses would be a germanium selenium glass, where you have a given fraction of germanium that is combined with some selenium. And so in this case, the typical structure of this glass would be that you have some germanium. So those germanium are 4-fold coordinated. Those germanium typically will be connected to some selenium. it's more rare to find some germanium bonds, but those bonds are still possible. They are not completely forbidden. On the other hand, typically you will find some selenium bonds. And so the typical structure will be like this. So the structure will depend on the exact composition. It will depend on what is the fraction of germanium and the fraction of selenium. But typically, this structure is going to look like this, where you have some chains of selenium that are cross-linking some germanium like this. So you have those selenium chains like this that link together the germanium. So those selenium, they are all two-fold coordinated, so they form those chains, and the germanium are always four-fold coordinated. So the germanium are the cross-linking element that connect those chains together. So you would have some structure like this, where those selenium chains are connected to each other, and they tend to form some rings like this. And in the case of chalcogenide glasses, since unlike oxide glasses, you don't always have a selenium in between two germanium, or you don't always have a germanium in between two selenium, then typically when it comes to chalcogenide glasses, when we want to define the ring size, the size of the rings that are formed, where the rings are some closed path like this in the structure, where you start from one atom and you form a closed path to come back to the same atom. In this case, the size of the ring will be just given by how many atoms these rings comprise. So in this case, that would be an example of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That would be an 11-membered ring in this case. You count all the atoms to count the size of the ring. Another common example of chalcogenide glasses would be an arsenic selenium glass. In that case, you have the arsenic atoms that are the cross-linking elements that are cross-linking some chains of selenium. So same thing, you have some chains of selenium. They don't have to have all the same size. Some of them can be short chains with only a chain of length of 1. Some of them can have a length of 2. Some of them can have a length of 3, etc. So the size of the chain is fairly random in the structure, and it's going to depend on the composition of the glass. But in this is the same idea, that in this case you have those selenium that are forming chains and the arsenic that are cross-linking the chains together to form some rings. So that would be an example of another ring here, which is a closed path structure, a closed path within the structure, where you start from one atom and you find a closed path to come back to the same atom by jumping on bond by bond within the network. In the same thing as for germanium selenium atoms, typically in arsenic selenium, you rarely have arsenic homopolar bonds. They are possible, but they are not very common, especially when you have a low fraction of arsenic in the glass. On the other hand, you will have very commonly some selenium homopolar bonds. And of course, you will find some arsenic selenium bonds. So in chalcogenide glasses, like, you can have any combination of those elements. So for example, like you could also have a germanium arsenic selenium glasses, where you would have some germanium atoms that are four-fold coordinated, connected to some selenium atoms, where those selenium can be connected to some other selenium or to some arsenic. The selenium are usually two-fold coordinated. The arsenic is three-fold coordinated, etc. So you can have those types of structure where you have the selenium chain that are connected to each other with those cross-linking germanium or arsenic elements. So that's the general structure of chalcogenide glasses. And there can be some exception to that. You can sometimes have some homopolar germanium or some arsenic bonds. So there is always like some types of defects that can be formed in those glasses, but usually the structure of chalcogenide glasses will be made of those types of structure where you have the chain formed by the chalcogenide elements, some change of selenium or some change of tellurium or some change of sulfur atom. And this is typically what the structure will look like. You have those change of chalcogenide elements that are cross-linked with each other by some atoms belonging to column 14 or column 15, some atoms like germanium, arsenic, etc. Another important types of glass that is a chalcogenide would be a germanium, antimony, tellurium glass, or GSBTE, or commonly abbreviated as GST glasses. So in this case, you have a given alloy that contain a fraction X of germanium, a fraction Y of antimony, and the rest is tellurium. And in that case, that's a common type of glass because that's a glass that is used to store memory. That's a glass that can quickly, just like any memory storage, it can take two forms. It can be either crystalline or amorphous. And so this likes as a 0 or 1, like a transistor. And in that case, that's something that can be used to store memory by storing some bytes of information depending on whether this system is crystalline or amorphous. And in these types of germanium, selenium, germanium, antimony, tellurium glasses or GST glasses, those are some very common phase change materials. They can easily change from a crystalline to an amorphous state. And so this allows them to store information. So they can be used, for example, in like a disk, like to record memory, like DVDs or those kinds of discs that are used to store information. And these types of glasses is pretty important in that case. So in that case, the structure of those glasses would be that it's made of those germanium, which are still fourfold coordinated, that can be connected, for example, to some tellurium atoms that are twofold coordinated, and connected to some antimony that is like an arsenic threefold coordinated. So you have this kind of structure like this, where you will find some rings, some chains of tellurium that are interconnected with each other with some antimony atoms or some germanium atoms. So this is the basic structure of chalcogenide glasses. We will talk more about this, those types of glasses in this class. But for now, the most important is to figure out, based on the 8-n rule, what is the typical coordination number of each element, and then how those elements are connected to each other to form a glass. And then based on the structure of those glasses, what you can do is count the number of constraints per atom that you have, like what we have seen in the previous video on topological constraint theory, to predict whether, based on the connectivity of the glass, whether these types of structure can form a glass or not, depending on the number of constraints per atom that you would get in this glass. That's a common application of topological constraint theory to predict what would be, for example, in this case, the range of X and Y values for which this type of system would be able to form a glass, and the range of composition for which this type of system would not be able to form a glass.